All right, we've been over the basics, so now I can talk about the Gibbs free energy. This is the critical main focus of the thermodynamics chapter. So for this video, you'll need your calculator, and you'll need access to the thermodynamic tables in the Appendix J. I think it's Appendix J in the OpenStax. All right, so the Gibbs energy, it relates a couple of different things, okay? Entropy, which is the symbol S, okay? Enthalpy, which is a symbol H, and temperature, okay? And so we can calculate what's called the change in free energy, or the delta G, or the Gibbs energy, okay? And this will tell us if a reaction is going to be spontaneous or not, and what's the maximum amount of energy involved in that process, okay? So it depends on the chaos and randomness, and it also depends on the temperature, high, low, and it also depends on the fundamental types and numbers of bonds that are being broken and formed in a chemical transformation, okay? So G is normally in units of kilojoules per mole. All right, H is enthalpy in kilojoules per mole. By the way, I just want to point out, in case you've forgotten, we have delta H, that little circle thing. That little circle thing does not mean to the 0 power, it means standard state. Standard state is 1 atmosphere for gases, 25 degrees Celsius for the substance. Okay, I know there's a T in this formula. And the little circle is also for 1 molar concentration if you have salts or substances dissolved in a solvent like water, okay? T must be in Kelvin for this, to work out, okay? So T is always in Kelvin, as always, right? With gas laws, we saw temperature had to be in Kelvin, and same with thermodynamics. And S is in entropy, and I just want to note that we always have the numbers in the tables in units of joules per mole per Kelvin. So you've got to do some finagling there to get everything in kilojoules and your temperature in Kelvin, so that everything cancels out and gives you the answer in kilojoules per mole. Now delta H, this is a review. We've already talked about this in, I don't remember the chapter number, previously in Chem 111 last semester. The delta H for a reaction is the sum of the heat of formation of the products minus the sum of the heat of formation of the reactants, and we use the coefficients in place of N here in the balanced chemical equation. I'll show you an example of this because we need to do this, all right? So enthalpy of formation of elements, once again, is 0. The OpenStax textbook, I think, actually puts elements equal 0 in here. I never do when I hand out my tables in the physical classroom. You just need to memorize, if you're looking for sodium on the periodic table or in the table and you're like, what's the heat of formation of sodium? Well, what do you have to do to sodium to make it sodium? Nothing. Well, then there's no energy cost, because that's your starting point. That's the ground level that you're building off of. So the heat of formation of elements is 0. Remember again, if a reaction is exothermic, it produces heat. Okay, temperature, right? And that delta H is 0, or it's a negative number. And if it's endothermic, delta H is greater than 0, or it's a positive number, and that means it absorbs heat. All right. Now entropy is calculated in exactly the same way, so it's cool. I don't really have to talk about this too much, other than you're going to look at the entropy numbers instead of the enthalpy numbers. Okay. Now keep in mind that ions, elements, and compounds all have specific entropy values. So what's the entropy of lead? Well, that's going to be a number at standard state. What's the entropy of helium gas at standard temperature and pressure and so on? It's going to be much higher, because helium's a gas, lead is a solid, right? So when you're talking about randomness or chaos, we know that elements are going to have some entropy values just based on their crystalline structure or state of matter or whatever, okay? Oxygen's diatomic, there's more randomness there, because you could arrange those two atoms in different ways. There's going to be vibration, there's going to be rotation, whereas helium is just, you could think of it as a ball, not as much randomness, right? So helium gas and oxygen gas are going to have different entropy values. Now watch out for ions. So if you have sodium chloride aqueous, that might be in the table, or you might have to look up sodium ion in the table and then chloride ion in the table. All right. Keep in mind that it's state specific, so don't just look for Na. Look for sodium solid or sodium liquid or sodium plus, whatever state is in the chemical reaction you're operating on, okay? All right, so what the heck does Gibbs tell us? Well, Gibbs tells us the total energy cost or gain in a chemical reaction. And the Gibbs free energy tells us what is the maximum amount of energy that can be extracted from that process. So if we take a bunch of gasoline and we burn it, we know it gives off energy. How much energy? Well, the maximum amount of energy that's freely available for you to extract from that process of combustion is given to us by the Gibbs free energy. So it doesn't mean free in the term in terms of economy or business. Okay, so free doesn't mean it's like free like we think of when we go shopping or something, like buy one get one free. All right. Spontaneous reactions are going to be negative Gibbs. Okay, I don't care what the H, what the S is. This is the deciding factor. If the Gibbs energy is less than 0, it's spontaneous. If the Gibbs is greater than 0, it's spontaneous. I don't have it on this slide, but if Gibbs is equal to 0, it means it's at equilibrium and it's not spontaneous. It's just sitting there as well, okay? If you use this equation, you can get all of the nitty-gritty details that you need, okay? So make sure you write this equation down. Now, when is delta G going to be less than 0? It's going to depend on the signs of the values that you have, right? So delta G is equal to delta H minus T delta S. So if delta S is negative, you're going to have the minus and a negative, so that gives you a positive quantity there. But then how does it balance that negative delta H? Does it override it? Does it delta H win? You know, so here's a chart here showing you kind of a summary of all the different possibilities. Delta H can be negative or positive, delta S can be negative or positive, and then what the resultant delta G is. Now, sometimes it's a win-win situation. Delta G is less than 0 at all temperatures. That means it's like falling off a log. No matter what temperature you do this chemical reaction, it's going to happen. Probably, for example, throwing sodium into water, okay? Now, if delta G is greater than 0, it means that it's not spontaneous at any temperature, okay? So if you take carbon dioxide, I could be wrong about this, but if you heat it up to 1,000,000 degrees, it will probably never form carbon and oxygen gas, okay? Now, if both delta H and delta S are both negative or both positive, guess what? You are having a competition between delta H and delta S. Sometimes it's spontaneous and sometimes it's not spontaneous, all right? I'll let you write this down and think about it in more detail, and you'll see this as you work through your own practice problems. So you might want to know about these two cases that are kind of like, okay, when is it spontaneous? Is it at low temperature or high temperature or vice versa, okay? And we want to calculate, hey, what is the temperature? Now, I won't derive this equation for you, but it comes from the Gibbs. And temperature is going to be equal to delta H over delta S. So if you have a delta H value that's negative and your delta S value, H and S are both given to you, you can calculate the ratio there, and then you can find out what the temperature is at which it will be spontaneous or not spontaneous, okay? Now keep in mind, temperature is always positive. 0 Kelvin is the lowest possible temperature, but everything's going to be a positive number, so you can't have a negative number. So if you make a mistake and you plug in delta H is negative and delta S is positive and you get a negative Kelvin number, please do not write that down as a final answer. The kelvins are always going to be positive. If you get a negative Kelvin, it means you're trying to calculate the temperature of one of these top two cases where the delta G is going to be always negative or delta G is always positive. So just pause and think about, hey, is delta G negative or positive, okay? But if you're in this situation here on this slide, it's reasonable to calculate the temperature of your change. All right, let's look at an example. So at what temperature will the following reaction be spontaneous? So we've got iron oxide, we've got hydrogen gas forming iron metal and vapor, right? Water vapor or steam. And we're given delta H is plus 98.8 kilojoules per mole and delta S is plus 141.5 joules per mole. So they're both positive, all right? So we can take a positive and divide by positive and get a positive Kelvin temperature and figure out what temperature that is. The first thing you want to do before you do the division is convert the entropy to kilojoules per mole. And we do that by dividing by 1,000. So move the decimal over 3 to the left and you get this number here, okay, in units of kilojoules per mole per Kelvin, Okay, those are the units for entropy. Now what you want to do is use that fancy equation here. The temperature is delta H over delta S, and so you plug that into your calculator and you get 698 Kelvin. If you're interested, 698, if I can punch it in correctly, minus 273.15 is 425 degrees Celsius. So that's about the temperature easily achievable by a Bunsen burner, for example, okay? So that's the minimum temperature. What does that mean? Well, you have to be this temperature or hotter for this reaction to proceed. We are not making any claims about the kinetics. If it's going to be fast or slow, we're just saying that, it can happen. It would be spontaneous. Example 2, calculate the standard free energy change for the following reaction at 25 degrees Celsius. So we got iron 3 oxide once again. We've got carbon monoxide as reactants. On the product side, we have iron metal and, let's see, carbon dioxide gas. And my gosh, they don't give us any information. So what do? Well, plan your attack. We know we need to calculate delta H for this reaction. Then we need to calculate delta S for this reaction. Then we have to use the Gibbs to calculate delta G. Okay? So it's kind of like 3 problems in one. This is like, your final exam kind of question because it reviews enthalpy, entropy, and everything else, okay? So we first want to grab our delta H reaction, and we want to write out the formula here, okay? It's always going to be products minus reactants. And remember, products are on the right-hand side of your chemical reaction. So first, the N. What do you do with the N? Here's where you use the N. Now we have a 2 in front of the iron, so it's going to be 2 times the heat of formation of iron, okay? Plus, okay, that big huge epsilon or summation sign means add them up. So we're going to have 3, because we have a coefficient of 3 in front of the CO2, 3 times the heat of formation of CO2, all right? Then we subtract, because there's a subtraction in the formula here, right? There's a big old minus sign there. Then we do the same thing for the reactants. Now reactants, remember, are on the left side of the chemical equation. So we have 1 rust molecule, right? So 1 times the heat of formation of iron 3 oxide plus 3 times the heat of formation of CO. All right? So that's all set up there correctly. Now this is where I was wrong. It's not J, it's G. Grab your OpenSticks chemistry textbook or get the PDF online. And this is where you want to find out, hey, what is the heat of formation of iron? Oh, that's an element, it's 0. But what about CO2 and these other compounds? Well, they're going to have real values. So you plug those all into the equation. It's a matter of just looking them up and all that. And then you do some math. Now you're going to have a double negative on the right, so be careful about that. I like to do all my grouping in those little brackets there before I do the subtraction. And then at the very end here on the bottom of this slide, you can see how I have the double negative there. We're subtracting a negative number. It comes out to negative 24.8 kilojoules per mole. What does that mean? That's the heat of reaction. It's exothermic. It releases that amount of heat. Next, we calculate the change of entropy of this chemical reaction. Same kind of formula, products minus reactants. So we have 2 times the entropy of iron. We have 3 times the entropy of CO2, and those are all products. So remember again that the products are located on the right-hand side of the chemical equation. Then we subtract, because there's a subtraction in our formula, and we have 1 iron 3 oxide, and we have 3, right, entropy of CO, okay? And again, CO is going to have a different entropy than CO2 because they have different shapes and sizes and vibrational modes and everything else, okay? Now, what we do is we use Appendix G. It's that same appendix. You're going to have the entropy values in that table. Check the YouTube link, by the way. I'll make a link to the Appendix G. And you plug in all those values. Now here I just want to point out that iron itself, which is a solid substance, it's an element, it does have an entropy of 27.3, okay? If you look at CO2, bigger number, 213.6. Why is it so big? It's a gas, right? CO2 is a gas. If you compare CO2, which is 213, with CO, which is 198 or so, 213 is a bigger number than 198 because CO2 is a more complicated molecule than CO. CO is linear, CO2 is trigonal planar. Anyway, there's a lot of detail in there, but let's just go ahead and do the math, do the calculations. And what I find is we have a value of plus 15.2 kilojoules per mole. So when we're going from left to right in this chemical reaction, delta S is positive. What does delta S positive mean? It means more chaos, more randomness, more disorder, more entropy, higher entropy. Okay? So in going from left to right, this is entropically favorable. Before we use the Gibbs, we do need to convert this to kilojoules per mole per Kelvin. So again, just divide by 1,000 on your calculator. 15.2 divided by 1,000. I wrote that down. And I'm putting a little plus sign there just so I make sure that I know that it's positive. Okay? Now we use the grandiose Gibbs equation. It's going to be delta H minus T delta S. So the T is 25 degrees Celsius. Wait, before you plug this into the Gibbs, please add 273 to it. Sure, you can add 273.15, but you're going to round to the ones place. So I get 298 Kelvin, okay? Make sure your temperature is in Kelvin, because do you see the entropy units? Kelvin, Kelvin cancel. And so what you get as a final answer here is negative 20.3 kilojoules per mole. So that right there is the maximum amount of energy that you could extract from this process. The fact that it's negative means that, hey, we might be able to process iron ore in this fashion to make some iron for making steel and whatever else. Okay? Delta G negative means it's spontaneous. We would not know otherwise. In summary, use Appendix G in your OpenStax chemistry textbook for all of these data values. Delta G is equal to delta H minus T delta S. Two things. Temperature has to be in kelvins. Entropy must be in kilojoules per mole per Kelvin. Forgot the K there. Because the units will all cancel and you'll get the delta G in kilojoules per mole. All right? Delta G is the heat of formation of the products minus the heat of formation of the reactants. Make sure you use the coefficients in the balanced chemical equation for this formula and the entropy reaction, the entropy formula, okay? So entropy and enthalpy, same thing, just different numbers, okay? And the last thing I showed you was temperature is equal to delta H over delta S, and you use that equation only when you have a mixed situation, when one is plus and one is minus, and the other way around, okay? If delta H and, when delta H and delta S are both positive or both negative, they're competing against each other, so you use this formula. If one's plus and one's minus, or the other way around, you can just trivially look at it and see that, oh, delta G is always going to be negative, or delta G is going to always be positive. Thanks for watching. I know it was a lot. You might have to review and take notes carefully on this. Please like, please subscribe. Have a great day, everybody.